like gravitational waves for a while. This is at MIT working on relativity. And today we're glad to have him talking about gravitational waves, black holes, and exoplanets, and astrostatistics journey.
Okay. So my thought here was to tie together kind of three very disparate topics with yet another thing that people don't often think of as an important topic, but I think really is astrostatistics. So I'm going to talk about gravitational waves, and then I'm going to talk about likely gravitational wave sources and what we know about them electromagnetically, which is a pale shadow of what we can learn about them from gravitational wave signals. And then I'm going to jump back to gravitational waves and show how some techniques that we use to analyze gravitational wave signals are also useful in investigating the formation environment and the influence of local stellar density on the formation of exoplanets. And so I'm calling this an astrostatistics journey because the thing that's going to let me hop back and forth is I'm going to be exploiting statistical techniques that were used in one domain in another domain. So to start, gravitational waves. Many people here are going to be very familiar with some of this material, but I'm going to go through a review so everybody's on the same page. Much like electromagnetic disturbances are produced by accelerating charges, gravitational waves are produced by accelerating masses. They propagate at the speed of light, and they interact very weakly with matter, because the gravitational constant in dimensionless units is so much smaller than the electric charge. So that makes them a fantastic observational tool. They are not reddened by dust. They are not obscured. They do not undergo any of the troublesome effects that we see with the electromagnetic spectrum. On the flip side, that makes them a horrible observational tool because they do not interact with your detector either. So a lot of the challenge in detecting gravitational waves, and in the collaboration that I'm a member of, the LIGO collaboration and its European counterpart, the Virgo collaboration, a lot of the challenge is producing a sensitive enough machine to detect these extremely weak perturbations from gravitational waves. The effect of a gravitational wave is just to produce some changes, periodic changes usually, in separation between two test masses. And unlike electromagnetic waves, they're a spin-2 wave. They come in two polarizations, but the polarizations behave differently than for electromagnetism. This is a picture of the periodic sequence of perturbations you would see in test masses from the plus polarization. You can see why it's called plus, because it perturbs in this way. And there is another polarization that's rotated 45 degrees with respect to this, where the perturbations go along these diagonals. A lot of sources in the universe could produce gravitational waves. The types of sources that I'm going to focus on in this talk are compact binary objects. So I'm talking about neutron stars in a binary, a neutron star with a black hole, or black holes in a binary, in the very last stages of their life, as they're inspiraling towards each other and finally coalescing over seconds to minutes. The frequency of those waves is roughly 1.5 kilohertz and scales in this way with the total mass. Okay, so if you want to build a detector that's sensitive to these things, it should be optimally sensitive somewhere in the few hundred to few thousand hertz range. And that is exactly what the LIGO detectors do. This is just illustrating, you can see here the signal that comes out of this type of event is quasi-periodic, but increasing in frequency as the objects spiral closer and closer and closer together. At the same time, its amplitude is increasing until there's a final catastrophic singular merger here, which is the sort of thing that a lot of people here work on calculating. I'm not going to discuss merger of two compact objects in this talk. I'm going to focus on the in-spiral parts, because that is the part that we can model the best and most efficiently today. That's not to say that the merger part isn't important, but that's just not going to be a focus of what I'm talking about. Here I'm showing for initial LIGO, so the LIGO detectors as they were 2 years ago before they were dismantled for an upgrade, the strain sensitivity power spectrum, the strain sensitivity spectrum. So you can see here that at low frequencies, this may be a little bit hard to read, but this is 10 hertz, 100 hertz, 1,000 hertz, 10,000 hertz. At low frequencies, they are not very sensitive because the Earth moves. And when the Earth moves, your test masses move. Coming up towards about 40 or 50 hertz, they become quite sensitive, and what we call the bucket lives between about 40 hertz and 1,000 or 1,500 hertz. It's this region in here where they are optimally sensitive, tuned to detect signals from stellar mass objects undergoing an in-spiral. Skip that slide. This is a picture of the detector in Washington. There's a corresponding detector, LIGO detector, in Louisiana, and a Virgo detector in Italy as well. The structure of this is there's a building here that houses a laser that's sent through a beam splitter up and down these two arms, which are about 4 kilometers long. The laser light comes back and interferes, and what we see as a result of a gravitational wave is small motions, relative motions in these test masses at the end of the arms, which are mirrors, produce oscillations in the light. We read out the light and we see gravitational waves. The expected displacement, fractional displacement from a typical, let's say, compact binary inspiraling at 100 megaparsecs is about 10 to the minus 21. The arms are about 4 kilometers long, so when you work it out, we're talking about absolute displacements that are like 4 times 10 to the minus 18 meters. So an atomic nucleus is, 500 times larger than this. So obviously this is an extreme technical challenge. It's a big engineering challenge to build an interferometer that is sensitive to these minuscule displacements. And sadly, I'm not going to talk about that at all because that's not what I do, but there are some really fantastic new developments that people have been working on for LIGO that have managed to achieve this limit, and in the next few years will actually push it much further, about a factor of 10 in sensitivity in that sensitive frequency range. Something that is very useful for us trying to extract information from gravitational wave signals is the detectors do not have a uniform sensitivity pattern on the sky. A detector like this, these black arms indicated here, has this, roughly speaking, sensitivity pattern, this peanut-shaped thing, to the plus polarization, and this sensitivity pattern to the cross polarization. If you have a plus polarization wave that's coming in at 45 degrees here, the relative displacements of the mirrors are 0. They move, but they move in synchronous, move synchronously, and so there's no net gravitational wave signal out the interferometer port. And we exploit that to try to determine the location on the sky of gravitational wave signals. Because if we know roughly the amplitude of the signal in each of the 3 detectors, and we know roughly how sensitive the detectors are over the sky, then we can back out allowed and excluded regions on the sky where the signal could and could not have been to produce the signal strength that we saw. I should mention, and this is a kind of a general astrostatistical point, the types of signals that we are expecting are very different than what people who might be used to electromagnetic astronomy think of. And I don't mean that there's some kind of chirp in time that ends in a final coalescence. I'm speaking here about the way that our signal to noise accumulates with time. So here I'm just showing sort of a generic chirping waveform. It's fairly short, it terminates roughly here. This is the pure waveform. Here I've generated synthetic noise of about the right amplitude for the initial LIGO detectors, and I've injected this waveform into it. Now I should tell you this, which to the eye doesn't look like anything, is a screamingly loud signal-to-noise ratio of about 20 signals. So this is easily detectable for us, but it is not as simple as if you are an electromagnetic astronomer of looking at a picture and saying, there is a bright point, I know that that is an object. We have to do data analysis, fairly complex data analysis, matched filtering or something like it, that exploits the fact that we know exactly what this template looks like in order to pull it out of this noisy data. Because in any given frequency bin or in any given time bin, our signal to noise is much, much less than 1. We can only get a signal to noise of 20 by accumulating signal to noise coherently over a long stretch of the signal.
These two plots are the same signal?
Actually, as it turns out, I thought that I generated the same, but this is expanded by a factor of 2. So this fits right in there. Okay, so before we start spending all this effort to extract gravitational wave signals, let's ask what's actually likely to be out there. So the current state of the art which has not changed much since it was published in 2010, is based on a combination of electromagnetic observations imposing constraints on population synthesis type calculations that tell you how many neutron star binaries, neutron star black hole binaries, and black hole binaries you expect per megayear per Milky Way equivalent galaxy. Now, sadly, the constraints that our electromagnetic observations place on these rates are fairly weak. You can see here that there's between 1 and 4,000 neutron star mergers per megayear per Milky Way equivalent galaxy. And there's similar types of uncertainties on these other rates. If you translate this physical rate into this detection rate, for initial LIGO, you get something that's negligible to order 1, and again, negligible to order 1, negligible to order 1. Even though these rates are intrinsically very different, as you go down this graph, the signals get much louder, so you can see them much further. And that's why, roughly speaking, these numbers are all comparable, even though these numbers are not. The LIGO detectors are currently undergoing an upgrade called Advanced LIGO that should turn on, get first light, I guess you'd call it, or at least first science light, in late 2015. And the sensitivity of Advanced LIGO is anticipated to be a factor of 10 better than the sensitivity of initial LIGO. Because we accumulate our signal to noise coherently, if our sensitivity goes up by a factor of 10, we are a factor of 10 more sensitive in amplitude, not energy, but amplitude of the signals, which means a factor of 1,000 more sensitive in volume. So roughly speaking, this column is about 1,000 times this column. And you can see that we're starting to talk about serious numbers here. Yeah?
Could you walk us through briefly where that uncertainty of factor 4,000 neutron star rate comes from?
Yes.
Are you going to do that?
I will do it for you right now in a few sentences.
Obviously, there's somewhat an issue with small number statistics. Number of
Right.
lines, right? Now, the factor 4,000 is sort of
The thing that is hard, so this rate is very sensitive to the total number of systems that you would expect to be at the very, very, very low end of the pulsar luminosity function. As far down, as I understand it, as far down as pulsars have been detected, the luminosity function does not turn over.
well, okay.
So depending on what you assume about those undetectable pulsars and which population synthesis you would like to trust that matches the detected pulsars, you get this kind of uncertainty. That's my 2-minute overview understanding of this uncertainty. Now I should preface that with I'm not a population synthesizer, nor am I a pulsar observer. So this is repeating what I have been told by the folks who actually do this stuff for a living.
I guess I'll ask the same thing in a way that 4,000 per megayear, how many neutron stars are born per megayear?
Per megayear per Milky Way equivalent galaxy, that's a good question. So,
Just single neutron stars?
yeah, so the star formation rate is about 1 per year.
Yeah, it's not that much higher than this number, right? But this requires a double neutron star, which are close enough to this high.
Yeah, although you do have starburst galaxies that form at orders of magnitude higher rates. And we are sensitive out to, well, for advanced LIGO, we're sensitive out to, quarter gigaparsec, depending on what your system is, 300 megaparsecs. So it includes a significant number of galaxies that are forming at very much higher rates than the Milky Way. So I suspect some of that is where that is coming from, but, I'm not trying to say, by the way, that this number is what you should believe. This paper actually does a very nice job of breaking things down into pessimistic, fantastically optimistic, and sort of the middle of the road. And roughly speaking, middle of the road for this would, I think, be somewhere in the 1 to 200 range. Okay, so to extract astrophysical information from these signals, of course, a lot of the focus of the collaboration is rightly on just detecting gravitational waves, because the first detection of gravitational waves is, a fantastic discovery. But most of the people, maybe all of the people in the room, are astrophysicists, and we want to know about the astronomical side of things. And in order to do that, we need to know what sort of objects cause the waves. which means we need to estimate their parameters. So I'm just giving you a table here of all of the parameters, the properties of the system that go into influencing the waves. So the first and most dominant are the masses of the two objects, M1 and M2. We sometimes rephrase those into the chirp mass, which you can think of as sort of like a total mass, and a mass ratio. This controls the length of the signal, that is how much power is radiated and how quickly the objects come together, the strength of the signal, again because the power radiated, and also the coalescence frequency, the frequency at which the objects actually merge when the signal turns on. In addition, astrophysical objects carry angular momentum, spins. That's encoded in two angular momentum magnitudes, and then orientations with respect to the orbit if the objects have not had time to torque each other into alignment with the orbit. And it's quite likely that many astrophysical objects will not have had such an opportunity, so we expect there to be many misaligned spinning in spirals. The spin modulates the waveform because it causes the orbit, if the spins are misaligned, to precess. And as the precession happens, we receive different polarization components at each detector as the orbit wobbles. And the different polarization components the detectors are differently sensitive to, and so what we see overall is a waveform modulation. Spin can also accelerate or delay coalescence by acting sort of as an angular momentum reservoir for the orbit, and either holding up or accelerating the in-spiral. There are also, we call them extrinsic parameters, because they're things that are not intrinsic to the system. There's a location on the sky. That also feeds into our detector sensitivity and the polarization components. There's a distance and inclination of the orbit, a particular time of coalescence or reference spot on the orbit. And then there's sort of nuisance parameters, that's extrinsic parameters that you need to properly specify the waveform, but that no one actually cares about, such as the waveform phase at some reference time, where the object's in their orbit at GPS time 0. And then a polarization angle that just describes the rotation of the orbit on the sky, which completes the final mapping from orbit coordinates to Earth coordinates. For example, this is the same sort of waveform I was showing you before with the generic chirping pattern, but now in the presence of spin, and you can see what I was talking about, the waveform gets modulated because of the precession of the orbital plane. And what we are trying to do, what we try to do, is to match our data to this modulation, and therefore infer what the spins of the objects were and what their orientations were. So how do we do that? How do we actually estimate parameters from these things? I believe this is actually a highly unequal mass ratio. It's something like a neutron star into a 20 solar mass black hole. And I think the black hole is spinning at about 0.7, maybe 0.6, and it's very misaligned. The neutron star is not spinning, but this doesn't look, actually, there should be, never mind, if it were the signal that I thought I was just thinking of, there would be a null somewhere in here. So I think this is actually, must be less misaligned. It must be only like 20 or 30 degrees misaligned. Yeah. Okay, so what we're given from the detectors is a stretch of data. It contains both signal and noise. And the way that we estimate parameters is first we just pick 15 choices. We pick the spins, we pick the orientations, we pick the masses, etc. That gives us a reference signal. If you subtract that from the data, what's left has to be noise. And if you'll recall early in the talk, I showed you a plot of what the noise power spectrum looks like in LIGO. Most of the data coming out of LIGO are noise, so we like to think we understand our noise quite well. That's not completely true, but we can pretend. So we can compute then, for that choice of parameters, what is the probability, the likelihood, if you like the terminology, what is the probability we would get the data we saw? And that is based totally on the statistical properties we expect for the noise. And then we repeat this over and over and over and over and over again, building up a full probability distribution in the 15-dimensional parameter space using Bayes' rule to relate the likelihood to the posterior. So we get a distribution on the 15-dimensional parameter space given the data we saw, how likely each parameter set is. Now 15-dimensional spaces are hard to explore. You can't just grid it up, 10 points in this dimension, 10 points in that dimension, 10 points in this dimension. Pretty soon you're talking about serious computing power. So we use tricks, and this is where the Astrostatistics enters. We use tricks to explore the distribution. The trick that we use most at Northwestern, and largely through the parameter estimation group in LIGO, is called Markov chain Monte Carlo. And it's a random sampling technique that attempts to draw samples from this distribution. So rather than grading the space up and plotting the distribution, we're just trying to grab 15-dimensional vectors drawn from this. And the way that we do that is by proposing these 15 parameters, computing this quantity, then proposing a new set of parameters related to the old one by a jump proposal. So maybe we decide to change the mass a bit. Compute this quantity again, and then stochastically accept or reject these proposed parameters, wandering randomly in parameter space according to a rule that's designed in the long run to give us samples from this distribution. Okay, so it's a stochastic sampling method, and it's proven to be quite efficient at exploring these high-dimensional parameter spaces. So here I'm going to play a video of an MCMC analysis of a signal like this. And I'm showing you the parameter space in the mass 1 and mass 2 and the two-dimensional M1 and M2 plane. And you will see samples as the sampler wanders around in this plane and eventually finds a good location and then explores the peak of the probability of the good location. Yeah?
These initial probability densities that those requires.
Which initial probability densities are you?
The first frame.
Oh, the first frame, I think those are just thick lines to show you exactly where, sorry, go back. No, not there. The first line, these may be the very first samples that we've done. They might just be junk noise. There's this period that we call burn-in, where the chain, because we don't actually know what the right answer is, or we'd start the chain there. So the chain starts somewhere randomly in parameter space and wanders in the wilderness for a while before it finds the likely spot. So I'm guessing that what you're seeing here is just burning. All right, let me play that now. Okay. So you can see the chain wanders for a while, and then it eventually finds a good spot. And this is just a plot of sample number versus M1, sample number versus M2. You can see it's basically centered on the red line, which marks the location of the signal that we actually injected. It wanders around stochastically. It wanders into this correlated shape in the M1, M2 plane. This is not a nice round blob. Instead, it's this elliptical thing here that actually reflects the fact that what we measure is chirp mass and mass ratio, which are nonlinear combinations of M1 and M2, and give you this sort of sweeping line. And then if you project the chain down into 1 dimensions, you get these nice one-dimensional PDFs in M1 and M2. This much uglier plot is a 15 by 15 matrix showing you on the diagonal all of the one-dimensional distributions we get, and then in the rest of the matrix, all of the one parameter versus another parameter distributions. You see that some of them are these nice little circular blobs, which means the parameters are uncorrelated. Others of them have a lot of structure. They have a blob here, and a blob there, and a blob there, or a blob here, 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 etc. And you can imagine now this is just two-dimensional slices through the 15-dimensional parameter space. The whole thing is quite chopped up into little bits and very hard to sample.
So the one bit is actually separate blocks, or is this just a periodic parameter?
I think this piece here is actually periodic. Let me look at the parameter label. This is definitely separate blocks. This piece here and there are not periodic with respect to each other. Some of the other parameters, this is obviously periodic. It's just a wrapping. These stripes here are sort of quasi-periodic. That happens to be a degeneracy of in-spiral phase and polarization. We look at these things a lot, and we can tell you more or less what the physical effects are that are causing them. And we try, of course, to design our jumps according to those physical effects. So we're trying to explore 15-dimensional parameter space. It's quite expensive computationally. We want things to be efficient. And the key to efficiency is when you propose a jump, you want to have a good chance that it's going to be accepted according to your stochastic rules, so that's largely what we focus on. There's been a code under development as part of the LIGO algorithms library, largely developed at Northwestern, but also with collaborators around the world in collaboration. It's called Bailyn MCMC, and for people who like buzzwords, it's a parallelized, parallel-tempered Markov chain Monte Carlo that's capable of differential evolution and correlated jumps. That just means it's kind of fancy. Okay. So a big event, so to speak, at the end of the last LIGO run, before the detectors were shut off, undergoing upgrades for advanced LIGO, was a blind injection in September of 2010, which is not too long after I got to Northwestern. It's perfect timing. There was a signal injected into the 3-detector network, the one in Hanford, Washington, Livingston, Louisiana, and Virgo in Italy, that was blind. So a few people in the collaboration knew that this was an injection, but to everyone else, this was just data coming out of the detector. Could have been a real signal. The goal was to test our pipelines end to end. Can we detect the signal? Can we estimate its parameters properly? Can we all sit down in the same room and write a paper about it? And the answer to all those questions was more or less yes. By 6 months later, we had a publication ready to go. And at our big collaboration meeting in March 2011, we opened the envelope and discovered that this was a fake signal and was not an actual gravitational wave from a real astrophysical source. At which point, we all patted ourselves on the back. But if you want to read more about the type of parameter estimation that went on, this was published as part of this report on the search for compact binary coalescences just this last year. It only occupies a few paragraphs in that paper because it's not real astrophysics, but it's a useful test to show that we really can do what we're claiming we're able to do. I'm going to skip those. Okay. So I'm going to very briefly advertise what some of my colleagues at Northwestern do in the LIGO group, and then I'm going to move on to showing you what our current EM electromagnetic constraints are on one type of likely LIGO source, and how some of the tricks we've been employing in this parameter estimation can inform our understanding of the electromagnetic constraints. So some of the other things that we've been doing at Northwestern, we have a postdoc, Tyson Littenberg, who works, among many other things, basically on better noise models. Now, this sounds horribly boring, I'm sure. Who wants to know what sort of noise is coming out of your detector? But it's absolutely essential for what we do. Because the detector is full of glitchy data. It means it pops and it skips and it burps, and there's all kinds of modes in the mirrors and the suspension of the mirrors and everything else. And if one of those happens during a real signal, we don't want it to throw off our parameter estimation. We don't want it to look like some modulation from spin or some other signal that we would interpret as physical. Also, there's more gentle non-stationarity of the data. That is, it's not always having the same power spectrum that I showed you earlier. The power spectrum drifts over 100 or 200 seconds or so. In the advanced LIGO era, we'll have neutron star signals that last for tens of minutes. And if your detector noise is drifting over tens of minutes, the parameter estimation problem becomes rather challenging. So Tyson spends an awful lot of time working on those things. Ben Farr, who is not a relative of mine, but it's a lot of fun to share a group with him, is a graduate student, and a big part of his thesis will be on actually breaking our parameter estimation. Rather than doing the full 15-dimensional problem, doing quick and dirty estimation in, say, masses and spins and so on, and then really good estimation of sky locations. The goal here, and this is something a lot of people in the LIGO collaboration work on, the goal here is to do rapid sky location, localization of sources. So maybe even with a neutron star, a few minutes after the coalescence happens, we can have an accurate sky position and report that to people who are looking for gamma ray bursts or gamma ray burst afterglows and so on.
What do you mean by accurate?
So depending on what type of signal you get, we can localize things if it's in a favorable spot in the sky and it exhibits some precession, so it's neutron star black hole and spiral, say. We could do a few square degrees in the best case. More typical things are probably 10-ish square degrees, and occasionally we'll get really unlucky and be 100 square degrees. So what we're really talking about is, not that they would necessarily listen, but calling up LSST or something like that and saying, could you please, make sure that you don't have clouds when you're tiling this spot in the sky tomorrow night. Ben, because he's involved in this type of project, is looking at doing things that are like joint electromagnetic and gravitational wave fits. So we get masses very accurately. We do not get inclinations very accurately. If you see a GRB, you already know that you're more or less on axis within whatever the opening angle of the jet is, but you don't know what the masses were. You put those two things together, and pretty soon you start knowing just about everything about the system. Carl Rodriguez is another graduate student in our group. is performing right now a systematic study of how accurately we'll be able to do neutron-star parameter estimation in advanced LIGO, particularly focusing on some noise effects that can cause us a lot of trouble in determining masses. So everyone would like to be able to say, this was a 1.4 neutron star in spiral. And there are times when we may not be able to say that because of noise effects. Carl's is leading that study. And of course, we all work on code development and preparing our parameter estimation pipelines for advanced LIGO. Okay, so one source that I have talked about briefly is stellar mass black holes. And so what I'd like to tell you about now is some of our best knowledge from electromagnetic observations of the properties of the stellar mass black holes that we can see. And I'm going to try to convince you, first, that we know a fair amount, and second, that we know nothing, compared to what we would learn from a few LIGO detections. So the story that I'm going to try to tell you is how hard it is to learn things about these black holes electromagnetically, compared to how easy it is to learn things about these black holes in gravitational wave context. Okay, and this is a result of some work that I did in 2011, and then also a collaborator of mine, Laura Kreitberg, who was an undergraduate at Yale and is now a grad student at Chicago, and some other collaborators did just last year. Okay, so in fact, the strangest thing about black hole masses in X-ray binaries that we observe is a feature called the mass gap. So on this plot, I'm showing you an inferred mass function, that is probability distribution with respect to mass, for stellar mass black holes. And for those of you in the back, this is about 6 solar masses, this is 8 solar masses, 4 solar masses, 0, and you can see that it peaks somewhere around 6 solar masses. For a long time, there's been this lore in the field, all black holes are 7 solar masses. No, they're not quite 7, they're 6. It peaks strongly at 6, falls off rapidly towards the high end, and also rapidly at the low end. The mass gap is the fact that we don't observe stellar mass black holes in this region of the mass space. The heaviest neutron stars we see are just a bit over 2 solar masses. The heaviest theoretical neutron star you can really support is about 3 solar masses. And we don't start seeing black holes until 4, 4.5, maybe even 5 solar masses. So what's in the gap?
This is some inferred distribution with sort of selection built in, or is this?
This is an inferred distribution with observational errors built in, but does not attempt to model whether there are selection effects in the formation of low mass X-ray binaries that lead to a gap.
This is only using only things where you have more than just the mass function.
That's right. You have the mass function and ellipsoidal fit, and I'll explain in a minute exactly what that is. So some people have said that this might provide some kind of clue about what's going on in supernova explosions, in supernova explosions. Maybe either they succeed somehow and you're left with a neutron star down in this range, or they kind of sputter and fail and a bunch of stuff falls back and drives you up into this mass range. But the story I'm going to tell you is that this mass gap has a storied history, and up until a year ago was pretty rock solid. But Laura Kreitberg and I and some other people are arguing that now it may just be an observational effect of the kind that we were just discussing. And so I'm going to tell you about how the story is played out, and leave you with some tantalizing information that might suggest that LIGO could answer this question. Okay, so the history of the mass gap. The first person to write about the mass gap was Charles Bailyn and some collaborators in 1996. At this time, there were only 7 low mass X-ray binaries observed, and if you plotted the cumulative distribution of mass, you see that basically there is no mass below about 1, 2, 3, maybe 4 solar masses was about their 10% confidence level, and it shoots up here again with a peak somewhere between 5 and 7. Okay, well that's only with 7 sources. By 2010, there were 15 sources, and Farr, Özel, and collaborators undertook a study that tried to fit an exponential distribution. So a turn on at some minimum mass jumps up and then exponentially decays at high masses to this to the observed data. And the theoretical expectation was, of course, it would turn on at about 2 solar masses, where the heaviest neutron stars are. And then because we see black holes with 7 or 8 solar masses, it has to have a 7 or 8 solar mass decay constant, and then it just kind of tapers off to high mass. The actual result was something more like over here. It turns on somewhere around 6 solar masses, or maybe down around 4. And it has a scale length of only about 2 solar masses. So again, sharply peaked about 6 and falling off. A year later, I performed a study which suggested this is a plot of the minimum black hole mass. So probability distribution on the minimum black hole mass. This is giving a 90% confidence limit on the minimum black hole mass, which was about 4.2 in this particular model, which largely confirms those results, but it did a little bit more. In this study, we actually compared 10 different models for the black hole mass distribution against each other. And that's quite a challenging thing to do, particularly when the models you are in parameter spaces of different dimension. Some of them look like an exponential model. It has a turn on and an exponential decay. Some of them are power law models. They have a minimum and a maximum mass and a power law slope. Some of them were generic multiple bin histogram models. So the parameter spaces have different dimensions, and the parameters mean different things. Sometimes you have a minimum mass, sometimes you have a power law slope, etc. So trying to do this comparison properly is very difficult. And we employed tricks that we were starting to use in our LIGO parameter estimation in order to be able to do this comparison. In particular, we used a technique called reversible jump Markov chain Monte Carlo. In reversible jump Markov chain Monte Carlo, you actually jump between the different parameter spaces. So you might say my model right now is that I have this exponentially decaying mass distribution, but I'm going to jump to a power law with a slope of -7 and a minimum mass of 3 and a maximum mass of 10. And then you might jump next to a histogram, and then you might jump back to a power law, and so on. And so you're exploring sort of the product space of all of the different parameter spaces. And it's very challenging to do if you don't employ these tricks. So in particular, one trick that we employed was using interpolation. So first, we isolate ourselves to one parameter space, and we collect a bunch of samples. That's these little points here. You can kind of see the little dots. And then we use a data structure called a KD tree, which is drawn from computer science. It's a recursive subdivision, so you split your domain in half, and then you split that in half, and then you split that in half, and you split that, and you continue splitting your domain in half to draw these small boxes around the distribution. And the salient property here is you can see that where the points are dense, that is the center of this cloud, the boxes are small and squished together because you keep subdividing until you get around one point. Where the points are sparse, the boxes are quite wide open. So if you now pick a box at random, it is overwhelmingly likely to land in this dense region and not out here in this sparse region. And so you can interpolate your probability density that's represented by these points by just uniformly drawing a box at random. Okay, and so then we did that in another model space, and this is intended to illustrate that there might be a model space with 2 local maxima. Maybe it likes parameters over here, and it also likes parameters over here. And then in between, there's this wasteland with large boxes. And now if you want to jump from model to model, your jump proposal is just pick a box. And again, you're overwhelmingly likely to land in a good place, which means your jumps are likely to get accepted, which means your convergence rates are fast, which minimizes your computer time. Okay, so we use this in low dimensionality in the black hole mass work. It's harder to interpolate in higher dimensions, in LIGO, for example, but at the time I put an undergrad, very talented undergrad, Dan Stevens, on the job. And one outstanding physics and astronomy senior thesis award later, Dan headed off to Ohio State, and we got this type of jump proposal in our LIGO code, and it has greatly accelerated our analysis. So that's an example of the kind of astrostatistical crosstalk that I'm talking about between these two fields. Okay, so very quickly, I'm going to tell you why we think the mass gap might actually just be an observational effect. So from a theorist perspective, mass measurements, the mass measurements we used anyway, are all about this formula. So this is the mass of the black hole is given by F, which is the mass function, That involves measurements of the period of the system and the orbital velocity of its components, both things you can typically measure very accurately. So F is known extremely well. Q is the mass ratio of the system. Often the black hole is vastly heavier than its companion, so Q is often quite small. And I is the inclination. In practice, what this boils down to is F is known, Q is ignorable, and the inclination is the name of the game. Trying to estimate inclinations in these systems is hard, and also strongly influences the mass that you get at. So this is showing if you measure a mass function of, say, 2.8, that's this blue line here, but the inclination of the object is relatively small, the actual mass distribution lies up here somewhere around 6 to 8 solar masses. And a small change in the inclination can boost you even up here to 10 or bring you back down to 4. So as I said, the name of the game is measuring inclinations. The way that we measure inclinations is by looking at the tidally distorted companion in these X-ray binaries. So the companion has an oblong shape. It does not have a uniform surface brightness. And as you orbit, you are seeing different sides of it, depending on what your inclination is. If the binary is face-on, you're always looking down at the North Pole. If the binary is edge-on, part of the time you're looking at the sort of sub-black hole point of the companion, and part of the time you're looking at the anti-black hole point of the companion, and most of the time you're looking somewhere in between. And that produces these ellipsoidal variations in brightness. So both the shape of the variations and, more importantly, their amplitude can give you the inclination. If you're face-on, the amplitude of the variations is 0 because you're always seeing the pole. If you're edge-on, the amplitude of the variations is extreme. And so to match the inclination effectively, you're examining the amplitude of these ellipsoidal variations with orbital phase. However, the light that you see is not just from the star. There's also a contribution from an accretion disk, the accretion disk around the black hole, which may be subdominant, may be equal to, or maybe even larger than the contribution from the star. So this non-stellar light contaminates this signal and raises the overall level of the signal you observe, but does not contribute to the amplitude of the variations. So in effect, it makes the relative variation smaller. So if you do not properly correct for the non-stellar light, you would think that the inclination is larger than it should be, because the amplitude of the variations is smaller. If the inclination is larger than it should be, the mass you measure is also larger than it should be. I think I said that backwards, but in any case, the point is that you get a biased mass estimate. So here is an analysis by Andy Cantrell, who was part of the group at Yale that I worked with in some of this work, of one particular system that has been observed for about 30 years. And in this system, we have so much data that we can categorize it in two states, active states and passive states. And this is a histogram of estimates of the inclination that you would make in the active state, so these spots over here are active, these states over here are passive, and Andy's extremely careful analysis of this vast amount of data suggests the true inclination is somewhere around 51 degrees. So as you can see, you get bias toward much smaller inclinations when you are in the active phase. The active phase is when the disk is contributing more. And so this observational effect tends to bias your mass estimates. And then the question is, can we model it? And the answer, I'm going to skip over the details. The answer is yes. And when you do model it, the masses of some of the objects that we use in our analysis shift. So here's just a plot of the mass distributions that we used, the observationally inferred mass distributions that we used in our analysis to back out the overall mass function. And the dotted lines here are the uncorrected, that is not observationally modeled systems. And the solid lines, in particular the solid lines in these two systems, are the corrected values. And you can see that these two systems went from having masses that peak somewhere in the 5 to 10 range to having masses that are between 0 and 5. That is, they moved straight into the mass gap. And if you look at the minimum masses, so these two curves here, the dot dash curve is the original distribution of minimum masses from the uncorrected work. The dotted line here is the distribution of minimum masses that you would get if you ignored one system in particular. And you can see that both of them are basically equivalent. They say the minimum black hole mass cannot be much smaller than about 4 solar masses. But when you apply a correction of the Kreitberg et al. Paper, what you discover is that the minimum black hole mass moves down here comfortably into the range of the maximum neutron star mass. So in other words, the mass gap is filled up. However, the slides that I skipped over, there's an awful lot of statistical work in there trying to estimate exactly what the non-stellar light contribution could be. The accretion disk flickers in a correlated way. It does not flicker with white noise. And so all of these things are, a bit of complicated modeling that goes into this picture. And the point of all of this is just to say it's very, very hard to extract this information electromagnetically. It took 30 years of observing AO620 so that Cantrell and his collaborators could do the original, very careful analysis of that one system. Then we extrapolated from that system to correct all of the other 16 systems. Perhaps that extrapolation is wrong. Perhaps Cantrell's analysis, as careful as it was, is not right. So there's a lot of open questions here. And I should just say there's some more observational data currently in the pipeline that my observer colleagues are analyzing, so you should stay tuned. On the other hand, you can just wait for advanced LIGO, which can measure black hole masses from black hole inspirals to 10–20%, something like that. And so if there were a 3 solar mass black hole and a black hole inspiral, we would know about it almost, not immediately, of course, because it takes some time to analyze the data, but we would know about it a lot easier than 30 years of X-ray observations and trying to model all this other stuff.
So all these non-black holes are in X-ray binaries?
Yes.
Is the mass distribution of black holes in X-ray binaries expected to be related in some way to the mass distribution of the black hole neutron star binaries?
Yes, but we don't know in what way.
Or single black holes?
Yes, but we don't know what way.
So even if LIGO now finds binary black holes with 2.2 solar masses, that still doesn't resolve the X-ray binary.
No, it does not resolve the X-ray binary question, but it does resolve the question of whether supernovae intrinsically prevent black holes from forming from the mass gap. So yes, I'm not trying to say that LIGO is going to solve all of the electromagnetic observational issues related to this field, but it is a very useful alternative means of observing these systems. Yeah? Fire away.
Okay.
Shane, go ahead.
So do you have a plot of the inclination distribution before and after you correct for them?
I do not have it here. It is
in the paper?
I believe it's in the paper. I certainly have one and can show you afterwards.
And I know it's small-ish number statistics, but I've looked at it before, and I remember it is kind of biased towards higher, more edge-on inclinations, and you're going to make it even more
biased towards edge-on inclinations. I don't remember whether we even checked whether this effect was statistically significantly different from the old distribution. But I suspect it would not be, because really only 2 systems can move significantly. There were some other questions too.
Yeah. Well, how well can you tell the difference between a 3 solar mass black hole and a 3 solar mass neutron star?
That is a very complicated question to answer. I suspect we will be disappointingly bad at doing that from the perspective of people who expect to see gamma ray bursts going off versus black. It will be very, very difficult, I think, to tell the difference. There are people who work on it. It may yet be possible, but it is not an easy thing. Yeah.
When you correct the distribution for inclination, does it shift just the minimum mass, or does it significantly shift the peak of the distribution?
It did not shift the peak of the distribution, so this is actually, this sharp narrow thing is the uncorrected distribution. This sort of broad thing is the corrected distribution. So it broadened it, but it didn't really shift the peak. It was 2 systems out of 16. So
it's just that those 2 you expect the wrong inclination, or is it that you know them better than the others?
For various reasons related to the type of the secondary star in those systems, they were the most subject to non-stellar light contamination. Okay, in my last few minutes, I want to tell you now about a second project that's an offshoot of LIGO. And I'm going to go through this rather quickly, but I think it's quite a fun connection between LIGO statistics and regular astrostatistics. And the basis for this project was looking at those uncertainties in rates and saying, well, you know, in the optimistic case, advanced LIGO may have hundreds of strong signals, and that's great, okay? Problem solved, we're done, analyze those signals to death, let's work on that. In the less optimistic case, there might only be a few strong signals, but there's still going to be lots of weak signals. What I mean by weak signals are things that we look at them on their own, and we would not say that they are a 3 sigma, 5 sigma detection. Instead, we'd say they're like a 1 sigma or a 2 sigma detection. There's going to be a lot more of those than there are sort of these gold-plated 5 sigma. You know, you can now, on the particle physics standard, write the paper that says, we have detected this. And I am trying to argue, and I'm going to try to show you right now, that actually there is a lot of useful information in these weak signals. And so, you know, a catchy tagline for this is extracting information from undetected things. Okay? That's what I mean when I write that in my abstract. So the most basic thing you'd like to extract is just rates of events, right? How many things are happening per year per Milky Way equivalent galaxy. And our current state of the art, before this work that I'm talking about right now, was sort of twofold. One technique that had been developed is the loudest event statistic. That is, you consider the single most gold-plated detection in your data set, and you analyze the rate, assuming that this could be foreground or background. The advantage of that is the data sort of sets your threshold, right? You pick the loudest event. The disadvantages are you really only analyze one event at a time, so you're missing out on all of this information that comes from the sub-loudest events. Then the other state-of-the-art method is what you might call foreground dominated. This we're all familiar with. It's called counting. When you are sure that you have a sample of n events that are definitely a member of the class, if you want to estimate the rate, you count them up and you divide by the time. Okay. We want to handle, you know, sort of the intermediate regime where things are less certain. And so our approach was to allow each event to be assigned either foreground or background. So it just gets a binary flag, 1 or 0. You can parameterize the foreground and background distributions. These could be as functions of signal-to-noise ratio, as functions of mass, as functions of distance, as functions of, you know, anything that you want.
So that foreground is strong signals, background is weak signals.
Oh, I'm sorry, no. By foreground, I mean any signal. By background, I mean pops and glitches and hisses in your detector that masquerade as signals. I mean, at the 1 sigma level, there's a lot of stuff going on in the detector that, you know, looks like a signal. And then you just do a standard MCMC over both the parameters of these things. Maybe you want to fit the mass distribution of the foreground, and maybe you want to fit the amount of non-stationarity in the background, and also the foreground-background status of the event. So an output of this type of analysis is the following plot. So here I'm showing on the x-axis is signal-to-noise ratio. This is synthetic data. Since it's synthetic data, I know whether events are background detector pops or whether they're foreground gravitational wave events. Gray is background, black is foreground. And this vertical axis here is the probability calculated from an MCMC that the event was foreground. Okay, so the very, very loud events, the probability is 1 that they're foreground. The very, very quiet events, the probability is nearly 1 that they're background. But in between, you know, these events here, this is like 20% likely to be foreground, even though it is. This event is like 30%, 33%, etc. And the idea is that these events down here do actually give you some information. Okay, I'm actually going to skip over the rest of the discussion of this in the LIGO context. And I'm going to show you this in a different context. What I have here is a synthetic star field. And here, the foreground, can you see it, is a globular cluster that I have stuck in the field right here. The background is a spatially varying density with a gradient in this direction of stars superimposed on top of the globular cluster. And because I can play with my parameters, I set this up so that at the very center of the globular cluster, right here, in the center of the field, the densities, the spatial densities of the two are equal. So that means that there is no star in this entire field that has a better than 50% chance of being a member of this globular cluster. Okay, so there are no detected cluster stars in this field, in that sense. You could not, through any analysis, go through and say, that is not, that is not, etc. You cannot determine membership information. Nonetheless, using our technique, you can count quite accurately that there are just about 1,000 cluster stars in the field. This is the probability distribution on the number of cluster stars. The vertical line is the true value. And just about 10,000 background field stars. The vertical line is the true value. So even though we couldn't identify a single globular cluster star, it's obvious from this picture that there's 1,000 stars in the field. And we can also fit the properties of the globular cluster shape. So we can fit its sky location. It's centered at 0, 0, and then this is the x offset and the y offset probability densities scale to the scale size of the cluster. And you can see that we get the central location to a few percent of the cluster size, which is about what you'd expect if you had 1,000 stars. 1 over square root of 1,000 is about 3%. We do worse than that because some of them run into the background, so we don't get to 3%, we get it to 5 or 7%. But still, we get very reasonable statistical uncertainties in this picture. And then this is also a distribution of the cluster scale radius.
Do you need to know it's spherical?
Sorry?
Do you need to know a cluster is spherical?
You need to have a model for the cluster shape.
So if it has a stream, you wouldn't be able to.
If it has a stream and your model doesn't, you're out of luck.
You wouldn't show.
Yeah, but you could put in, if you thought it was tightly distorted, or you thought it had a stream, you could look for a stream.
So you don't know the orientation?
No, that's just another parameter. It's a stream, it's on angle, you can fit the angle.
But you should get out of your analysis whether your model fits the data.
Exactly. You can check. I mean, you can generate synthetic star fields basically from your model and go back and compare them to the data and see if they're reasonable. So if you were missing a stream, in principle, you can sort of subtract and try to see if there was some excess density.
It's really better than if I just do a profile figure of the galaxy, just go to that direction, and it's
Yes.
exactly excess.
And I can show you that in, well, actually, since you asked and I'm running a little short on time, let me just tell you quickly. This is a picture of the Kepler field. There are 1, 2, 3, and you can't really see it down here, 4 open clusters in the Kepler field. And an interesting question is whether the fact that the stellar density in these open clusters is dramatically enhanced with respect to the field influences the formation or evolution of planets about any of those stars. In order to conduct this analysis, though, you need to know, you need to be able to account for the fact that you don't actually know with 100% certainty which of the stars here belong to the cluster and which of the stars are just Kepler field stars. Now, in some cases you do, because the clusters have been surveyed and there are some known members. But as I'm about to show you, there are also members that the surveys have missed and that we can find. So the first step in this analysis, actually, this is for one of the globular clusters, or one of the, open clusters that has the most members. We took the Kepler input catalog, which is a survey down to about 23rd magnitude that is all the stars that all the stars that Kepler looks at are drawn from the Kepler input catalog. And the key point here is this was not a dedicated globular cluster survey, but using just spatial data from the Kepler input catalog, we could determine the center of this cluster. So this is the right ascension. The solid line is our right ascension distribution for the cluster center, and the declination distribution. And the blue dashed lines are the previous best fits from dedicated cluster surveys that try to extract certain cluster membership from this cluster and fit its location and its scale properties and so on. So my point here is we took the Kepler input catalog, which is not a dedicated cluster survey. We didn't use any photometric information. We didn't try to do main sequence fitting for this cluster or look for the turn-off or any of the other tricks that people employ to determine membership. And nonetheless, we do about as well at fitting the center of the cluster. And here I'm showing you the core radius of the cluster And this is the king parameter, which reflects the central concentration. We do about as well fitting all of these parameters just from the spatial distribution in the Kepler input catalog as people have done through dedicated analysis of the cluster, because we incorporate the uncertainties in this way. And I'm just going to leave you now with the tantalizing thought that I can tell you, though I am not going to show you, that the planet occurrence in Kepler data definitely differs between cluster and field stars. So that is suggestive that the stellar environment could be influencing the evolution of planets. But to determine whether planet occurrence actually differs between cluster and field stars depends strongly on Kepler selection effects, because the cluster fields are crowded, the stellar types are different, etc. And so currently we're building a fairly careful model of all the Kepler selection effects so that we can determine whether the intrinsic distributions differ or whether we're seeing a selection. And this type of analysis would not have been possible without first considering LIGO rates in the way that we did with this sort of fuzziness, what sort of information can you extract from the undetectable data. And I'm going to leave you with that. So, questions?
So you started motivated looking at these weak signals in LIGO data by considering the case of not having many strong sources. But no matter whether you have many or few strong sources, you will always be dominated by having even more weak sources.
Right.
So if you want to do statistics on probabilities of, say, finding black holes or so, we actually learn more from the fewer strong sources or from this much larger set of marginal detections or perhaps even non-detections in the
Right.
right.
So in this paper, we discuss exactly that issue. And it depends to some extent on the details of the place where the rates of detection of the background and foreground are crossing. So where you have about 50-50 probability. Exactly where that occurs and how rapid the rise in background is strongly influences whether you get more information out of the weak signals or more information out of the strong signals. Unfortunately, in LIGO, the background rises very rapidly, which suggests that you will get, marginal information. In the synthetic example I gave, you get about 20% better constraints on the rate uncertainty from including the marginal things. Now, that's nothing to sneer at, but it's not fantastic. In the globular cluster examples, of course, the fall off, or the rise, if you like, of the background, the increase in the field density compared to cluster density was a lot smaller. You got correspondingly more information. And the details of that will also depend on the kinds of pipelines that people design and how good they are at rejecting glitches and detecting marginal signals and properly weighting them against each other and so on. So I guess I'm saying I don't have a hard answer to your question. Yeah.
Could you say a little bit about the logic of choosing between models by jumping between them using the MCMC and how that's related to other types of phasing models?
Yeah. So what you are doing if you jump between models is effectively you're jumping in a sort of superspace which has various model parameters and one more discrete dimension that is 0, 1, 2, 3, 4, 5, whatever the models are. And if you then ignore all the parameter samples and you just count how many times you were in a particular model. I was in model 1 1,000 times, I was in model 2 100 times, I was in model 0 1 time, so on. Effectively, you are integrating out all of the parameters in each model. Right? You're just integrating over that whole parameter space. And I don't know if you're familiar, but the integral of the unnormalized posterior over all the parameter space is called the evidence. And it is, well, in this picture, it is the relative probability of the two models with respect to each other, given the data that you got. And so this is functionally equivalent when it works to computing literally the evidence of each of the models independently and then taking ratios. It can be more efficient than computing the evidence, which is sometimes hard to compute. It can also be dramatically less efficient if you don't jump between models very often. Yeah, that's the 2-minute summary. If you want to talk more, I'd be happy to discuss essence and implementing audio techniques for getting evidence.
So any more questions? Well, let's thank the speaker again, and we're heading off for the cookies. So.